You're listening to Worth Electronics What's Up Radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Worth Electronic technical specialists who are going to shine a light on some interesting topics, such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up podcast. It is back to school season, and very recently I was looking over some homework of a student, and they've just started classes in electronics and electronic design. Now, after talking through some definitions, it's occurred to me that I've never actually discussed the basics, and I am talking the bare bones definitions and explanations of components. Yes, we've talked about the basics of ferrites and the basics of transformer design, but what about a level below that? You know, what is a capacitor? And what is a diode? What is needed for an electronic application to actually run? So, if you've been in the electronics industry before, or if you're even a second level or a sophomore or above in electrical engineering, this podcast is not for you. In fact, you can actually reach out to our chat team directly at We Online and get some more intermediate and expert recordings. Today's podcast is for the new to electronics students, or even the professionals completely new to the industry and the world of electronics, whether you're a budding engineer or just curious about how your gadgets work. Specifically, today's podcast is dedicated to the new electronics students of Lake Area Technical College in Watertown, South Dakota, and to all other aspiring engineers. You have to start somewhere, and electronics are hard, but don't give up. We'll get through this together. So first, let's talk about the basics of electronic components. Now, at the heart of any electronic device, you have these components like resistors, capacitors, inductors, diodes, and transistors. And these tiny parts, they work together to control the flow of electricity, and then they perform various functions. So let's break down a few of these components, including the ones that Worth Electronic doesn't even sell. But it's okay, you can still find them online at DigiKey. So first off, we have resistors. Now, while relatively new to the product catalog of Worth Electronic, resistors are one of the most fundamental components in electronics. They play a very crucial role in limiting the amount of flow of electrical current in a circuit. You can think of them as speed bumps for electrons. Now, at their core, resistors are designed to resist the flow of electric current. And they do this by providing a specific amount of resistance measured in ohms. The higher the resistance, the less current will flow through the resistor. For example, if you have an LED that requires a specific current to operate safely, then you can use a resistor to ensure that the current stays within safe limits. In circuits with transistors or operational amplifiers, don't freak out, I'll get to those in a minute, but resistors are often used to set the operating point or bias of these components. This ensures that they function correctly within their intended range. Resistors can also be used to create voltage dividers, which are circuits that produce a specific fraction of the input voltage. This is especially useful for creating reference voltages or for interfacing different parts of a circuit that actually operate at different voltage levels. There are also pull-up and pull-down resistors, and these are used in digital circuits to ensure that inputs to logic gates settle at expected logic levels and they don't float. A pull-up resistor connects the input to a higher voltage level, while a pull-down resistor connects it to ground. Different types of resistors include fixed resistors that have a set resistance value. These are the most common type, and they're used in a wide range of applications. Variable resistors allow you to adjust the resistance manually, useful in applications where you need to fine-tune the resistance, such as in volume control. Thermistors, which are temperature-sensitive resistors used in temperature sensing and compensation. And light-dependent resistors, also known as LDRs, and these actually change their resistance based on the amount of light falling on them. Some parameters you need to consider with resistors include the resistance value, a fairly obvious parameter, but it determines how much the resistor will resist the flow of current. You also need to think about the power rating, because resistors dissipate energy in the form of heat. So the power rating, measured in watts, or capital W when written out, indicates how much power the resistor can safely dissipate without being damaged. Another parameter is the tolerance, or how much the actual resistance can vary from the state value. For example, a resistor with a 5% tolerance can vary plus or minus 5% from its nominal value. And finally, temperature coefficient. This indicates how much the resistor changes with temperature. Next, we are moving on to capacitors. Capacitors are another fundamental component in electronics. They play a crucial role in storing and releasing electrical energy. At their core, capacitors are designed to store electrical energy in an electric field. They consist of two conductive plates separated by an insulating material. We call that the dielectric. When a voltage is applied across the plates, an electric field develops and charge accumulates on the plates. The ability of a capacitor to store charge is measured in farads, capital F. Although most capacitors you're going to encounter in everyday electronics are actually measured in microfarads, nanofarads, and picofarads. Capacitors have a wide range of applications in electronic circuits, including energy storage, where they can help smooth out fluctuations in voltage. They're also helpful in filtering. In power supplies and signal processing, capacitors are used to filter out unwanted noise and smooth out voltage levels. For example, they can actually block DC signals while allowing AC signals to pass. This is useful in coupling and decoupling applications. Capacitors are also used in combination with resistors to create timing circuits. The time it takes for a capacitor to charge or discharge through a resistor can be used to generate precise time delays or oscillations. Caps are also great in radio frequency or RF applications because they're used in tuning circuits to select specific frequencies. And variable capacitors in particular are used in tuning radios and other frequency selective devices. The different types of capacitors that you might come across include ceramic capacitors, which are small, inexpensive, and widely used in general purpose applications. Electrolytic capacitors, which have a higher capacitance value compared to ceramic capacitors and are often used in power supply filtering applications. And tantalum capacitors, which are similar to electrolytic, but they actually offer better performance in terms of stability and reliability. They're also polarized, like electrolytic, so they have a positive and a negative lead, and they must be connected correctly in a circuit. There are also film capacitors, and they're known for their stability and low loss characteristics. They're used in applications requiring high precision and reliability, such as audio circuits and high-frequency applications. And then finally, there are supercapacitors. These ones need a little bit of care in TLC. You see, supercaps have extremely high capacitance values, and they're used for energy storage applications where quick charge and discharge cycles are needed, such as in backup power supplies and regenerative braking systems. Much like resistors, capacitors have a few parameters to consider when making your selection. The most obvious is the capacitance value, which determines how much charge the capacitor can store. There's also the voltage rating, and this indicates the maximum voltage the capacitor can handle without breaking down. It's important to choose a capacitor with a voltage rating higher than the max voltage in your circuit. Next, we need to consider the tolerance, and this indicates how much the actual capacitance can vary from the stated value. The equivalent series resistance, or ESR, is a measure of the internal resistance of the capacitor. The lower ESR values are preferred in high-frequency applications to minimize energy loss. And a final parameter is, of course, the temperature coefficient, which indicates how much the capacitance changes with temperature. In precision applications, capacitors with a low temperature coefficient are actually preferred to ensure stability over a range of temperatures. So to sum it up, capacitors are essential components that help store and release energy, filter signals, create timing circuits, and much more. And now we are moving on to inductors. I'm going to be honest here. This is one of the most popular components here at Worth Electronic. Inductors store energy, but you can't get them confused with capacitors. Inductors store energy in a magnetic field when electrical current flows through them. They're often used in filters and transformers. Inductors have a wide range of applications in electronic circuits. Now, much like capacitors, inductors can store energy, but they do so in a magnetic field rather than an electric field. This makes them useful in applications like power supplies and DC to DC converters, where they help smooth out fluctuations in current. Inductors are often used in combination with capacitors to create filters that block certain frequencies while allowing others to pass. For example, they can be used in low-pass filters to block high-frequency noise from power lines. Now, a little bit of our bread and butter here. Inductors are the building blocks of transformers, and these are used to transfer electrical energy between circuits and to step up or step down voltage levels. Transformers are essential in power distribution and many electronic devices. Inductors can also be used as chokes, which are designed to block or choke high-frequency AC signals while allowing DC or low-frequency signals to pass. And we use this in power supplies to filter out high-frequency noise. Finally, inductors can be used in radio frequency applications. We do this to select specific frequencies. They work in conjunction with capacitors to form resonant circuits that can pick out desired signals from a range of frequencies. Now, if inductors can be all of these things, then you would be correct in thinking that they do come in various shapes and sizes. First, we have air core inductors. These have no magnetic core, and they're used in high-frequency applications where core losses would be significant. They are simple and have a linear response, but are larger for a given inductance value. Iron core inductors use an iron core to increase the inductance. They're used in low-frequency applications like power supplies and audio equipment. The iron core can handle higher currents, but may introduce core losses at higher frequencies. Ferrite core inductors use, a ferrite core, which is a type of ceramic material with magnetic properties. Ferrite cores are used in high-frequency applications because they have lower core losses compared to iron cores. Toroidal inductors are wound on a donut-shaped core, and this helps to contain the magnetic field and reduce electromagnetic interference, also known as EMI. They are used in power supplies and RF applications. And then there are the multi-layer inductors. These are small surface mount inductors used in compact electronic devices like smartphones and tablets. They're made by stacking multiple layers of conductive material and insulating material. When selecting an inductor for your circuit, you need to consider inductance value, and this determines how much energy the inductor can store in its magnetic field. You also need to think about the current rating, which indicates the max current the inductor can handle without saturating or overheating. It's important to choose an inductor with a current rating higher than the maximum current in your circuit. The DC resistance, or DCR, is the resistance of the wire used to make the inductor. Lower DCR values are preferred to minimize energy loss in the form of heat. You also need to think about the saturation current, which is the current at which the inductor's core becomes saturated and it can no longer store additional energy. Operating an inductor beyond its saturation current can actually lead to a loss of inductance and increased core losses. A final parameter is the Q factor. This is a measure of the inductor's efficiency, defined as the ratio of its inductive reactance to its resistance at a given frequency. The higher the Q factor indicates lower energy losses and better performance in resonant circuits. All right, and now we go on to the diodes, and diodes allow current to flow in one direction only. It acts like a one-way street for electrons. Diodes are semiconductor devices that have two terminals, the anode and the cathode. When a positive voltage is applied to the anode relative to the cathode, the diode becomes forward biased and allows current to flow. So when the voltage is reversed, the diode becomes reverse biased and blocks current flow. This unidirectional behavior makes diodes very incredibly useful in a variety of applications like rectification, voltage regulation, signal demodulation, protection, and switching. Diodes are commonly used in power supplies to convert alternating current, AC, to direct current, DC, so AC to DC. This process is known as rectification. In a simple rectifier circuit, diodes allow only the positive or negative half cycles of the AC signal to pass, creating a pulsating DC output. And when we talk about voltage regulation, we're mostly talking about the Zener diode. And these are special types of diodes designed to operate in reverse breakdown mode. They're used to maintain a constant voltage across a load, making them ideal for voltage regulation in power supplies. Diodes are used in radio receivers to demodulate amplitude-modulated AM signals. If that sounds familiar, you're probably over the age of 25. Diodes are pretty special because they can protect sensitive components from voltage spikes. For example, a diode that's placed across a relay coil can prevent voltage spikes generated when the relay is turned off from damaging other components. And diodes are used in digital logic circuits as switches because they can quickly switch between conducting and non-conducting states, making them useful in those digital applications. We already briefly described the Zener diode, but what about the other diodes? First, we have the standard diodes, which are the most basic and used for general purpose rectification and switching applications. Zener diodes operate in reverse breakdown mode. Those are used for voltage regulation. And the Schottky diodes have lower forward voltage drop compared to standard diodes. This makes them more efficient in high-speed switching applications. Of course, one of the most popular diodes you may have heard about are the light-emitting diodes, also known as LEDs. These emit light when forward biased, and they've really grown in popularity over the last few years. We also have photodiodes that generate a current when exposed to light. They're used in light sensing applications like solar cells and optical communication systems. When you're selecting a diode, you need to think about the forward voltage, VF. This is the voltage drop across the diode when it's forward biased. Another parameter to keep in mind is the current rating that indicates the maximum current the diode can handle when forward biased, and the reversed recovery time, which is the time it takes for the diode to switch from conducting to non-conducting state. Faster recovery times are important in high-speed switching applications. Also take into account the power dissipation, which is the max power the diode can dissipate without overheating. And last, but certainly not least, because there are so many more components we did not cover, but we are going to discuss the transistor. These are the building blocks of modern electronics. They're used for switching and amplifying electronic signals. Now, transistors are semiconductor devices that can amplify electrical signals, or they can act as switches. They have three terminals: the emitter, the base, and the collector in bipolar junction transistors, or BJTs, or the source, the gate, and the drain field in field effect transistors. They're written as FETs, but they are also known as FETs. By applying a small current or voltage to one terminal, you can actually control a much larger current flowing between the other two terminals. This property makes transistors very versatile and essential in a wide range of applications. Transistors can amplify weak electrical signals, making them stronger. This is essential in applications like audio amplifiers, radio transmitters, and signal processing. They can also act as electronic switches, turning current on or off in a circuit. This is fundamental in digital logic circuits, microprocessors, and memory devices. Transistors can be used in oscillator circuits to generate periodic signals, such as clock signals in digital systems or radio frequency signals in communication devices. They're also used in voltage regulator circuits to maintain a constant output voltage despite variations in input voltage or load conditions. And in communication systems, transistors are used to modulate signals, encoding information onto a carrier wave for transmission. Here are a few of the most common types of transistors, starting with the previously discussed bipolar junction transistors, the BJTs. These are traditional type of transistors with the 3 layers of semiconductor material. They come in 2 different flavors, NPN and PNP. BJTs are used in amplification and switching applications. Next, we have our FETs, the field effect transistors, that control current flowing using an electric field. They come in 2 main types, junction FETs, JFETs, and metal oxide semiconductor FETs, also known as MOSFETs. FETs are widely used in digital circuits and power electronics due to their high input impedance and efficiency. Darlington transistors are pairs of BJTs connected together to provide high current gain. They're used in applications requiring high amplification. Insulated gate bipolar transistors, or IGBTs, combine high input impedance of MOSFETs with a high current capability of BJTs. IGBTs are used in high power applications like motor drives and power inverters. And then finally, we have the phototransistors. These are the transistors that respond to light. They're used in light sensing applications like optical switches and light meters. When it comes time to select a transistor, you need to keep these parameters in mind. First, the current gain. This indicates how much the transistor can amplify the input current. Higher current gain means greater amplification. Next, the collector-emitter voltage. This is the max voltage the transistor can handle between the collector and the emitter terminals. Ensure the transistor's voltage rating exceeds the max voltage in your circuit. Also keep in mind the collector current, which indicates the max current the transistor can handle through the collector terminal. And don't forget about power dissipation. That's the max power the transistor can dissipate without overheating. Finally, mind the switching speed. This indicates how quickly the transistor can switch between on and off states. Faster switching speeds are important in high-frequency applications. So let's wrap up what we've learned about some of these components. Again, these are the absolute basics and the roles of resistors, capacitors, inductors, diodes, and transistors. These components are the building blocks of electronic devices, and each plays a unique and crucial role in the functioning of circuits. We started with resistors, which control the flow of current and help in voltage division and biasing. Then we moved on to capacitors, which store and release electrical energy, filter signals, and create timing circuits. Inductors followed with their ability to store energy in a magnetic field and filter signals, among other uses. Diodes came along next, showcasing their ability to allow current to flow in one direction, making them essential for rectification, voltage regulation, and protection. Finally, we explored transistors, the versatile components that can amplify signals, switch currents, and generate oscillations. Now, understanding these components and their applications is fundamental for anyone interested in electronics. Whether you're designing a simple circuit or a complex PCB, knowing how to select and use these components effectively is key to creating reliable and efficient electronic devices. And remember, designing a PCB involves more than just placing components on a board. EMI mitigation, proper grounding, and a thoughtful layout, these are all critical in ensuring that your circuit performs well and is free from interference. If you enjoyed this episode, be sure to subscribe and leave us a review. If you have any questions or topics that you want us to cover, drop us a message on our social media channels. You can also find most of these components available at Worth Electronic online at www.we-online.com. Feel free to reach out to us online through the chat team or through your local field agent. We can get some free samples headed your way. You can find other components at distributor sites such as DigiKey and Mouser. You're listening to Worth Electronics What's Up radio podcast, where each week we're seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Worth Electronic technical specialists. We're going to shine a light on interesting topics such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up podcast.